We're going to talk about temperature. First, we're going to talk about the measurements that we use, and then we're going to find out what does it measure. When measuring temperature, there are three common scales that are used. They are the Fahrenheit scale, the Celsius, also known as centigrade scale, and the Kelvin scale. The Fahrenheit scale is pretty much used in America and very rarely anywhere else. The Celsius scale is used throughout most of the world, and we'll talk about how it was developed in a moment. And then the Kelvin scale is used in most scientific experiments. The Fahrenheit scale was the one that was first developed. This was developed to show how high the mercury rose inside of a thermometer at different temperatures. As the temperature went up, the mercury in the thermometer went up, and we were able to measure that. In the Fahrenheit scale, we can see that water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. When we look at the Celsius scale, you'll notice that the water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The reason for this difference in temperature is just a man-made division. The Fahrenheit scale was developed in the early 18th century by a German scientist named Daniel, I think if you can guess his last name, Fahrenheit. He didn't use water when he set the scale. He used a different substance that froze at what he called 0 degrees, so it became 0 degrees Fahrenheit. And at the high end of his scale, he used body temperature, which he set as 90 degrees Fahrenheit. That scale was adjusted slightly, and we ended up with what we now call the Fahrenheit scale. Then, in 1742, a scientist named Celsius developed a different scale. It's also known as the centigrade scale, and it uses 0 degrees Celsius as the temperature that water freezes, and it set 100 degrees Celsius as the temperature at which water boils. That was because that could be used anywhere in the world. And it didn't vary dependent upon the amount of salt that was in the mixture. It didn't matter what the temperature of that person was. It was very consistent. Water freezes at 0 degrees, and it boils at 100 degrees Celsius. The 100 degrees separation made it much easier to do calculations and numbers, and so a lot of people really liked that difference. Then we developed the Kelvin scale. Now the Kelvin scale, you'll notice, is very much like the Celsius scale. It has the same 100-degree difference, but it sets the freezing point of water and the boiling point of water at a slightly different temperature. You'll notice that water freezes at 273 degrees Kelvin and boils at 373 Kelvin. As you can see, the mercury rises the same distance, but the way that we mark them is what changes. Because these have different units, we will be able to do unit conversions. In this course, we will not be changing from Fahrenheit to Celsius or Celsius to Fahrenheit. We will be focusing on how to go from Celsius to Kelvin and Kelvin to Celsius. You will be expected to know which has a larger unit, the Celsius unit or the Fahrenheit unit. So let's start there. To compare the unit size, we may need to measure the same distance. In this case, we're going to look at the distance between how high the mercury rises when it goes from water freezing to water boiling. On the Fahrenheit scale, we see a difference of 212 degrees Fahrenheit and 32 degrees Fahrenheit. So 212 minus 32 leaves us 180 degrees Fahrenheit. And on the Celsius scale, we see that water boils at 100 degrees Celsius and freezes at 0 degrees Celsius, and the difference then is 100 degrees Celsius. Now we compare these, and we see that there are 180 degrees Fahrenheit for every 100 degrees Celsius. We're going to make this into a ratio, and we're going to see that for every 18 degrees Fahrenheit, there's 10 degrees Celsius, or for every 1.8 degrees Fahrenheit, there's 1 degree Celsius. What that means is there are almost 2 degrees Fahrenheit for every 1 degree Celsius. That means that the Celsius measurement is larger and the Fahrenheit measurement is a smaller unit. The reason we're not going to be converting between Fahrenheit and Celsius is because the Fahrenheit scale does not start at 0, so we have to take into account the addition of 32 degrees Fahrenheit into the calculation. We aren't going to do that in this class. But again, you should recognize that the Celsius or centigrade scale is the larger of the two units. When we look at the Celsius and the Kelvin scale, we can see that they are the same size of unit. The difference between 0 and 100 and 273 and 373 is each 100 degrees Celsius. So there is no conversion factor. We don't have to say there's twice as much. The unit is the same size in Celsius and Kelvin. But you'll notice that they do not start at the same place. That means one is always a higher temperature. 0 degrees Celsius is equal to 273 degrees Kelvin, so that means we have to add 273 to whatever Celsius temperature we have in order to find the Kelvin temperature. So Kelvin temperatures are always higher numbers and Celsius temperatures are always lower numbers. Let's talk a little bit about why the Kelvin scale came into being. For many years, the Celsius scale worked fine. It had a good range from 0 to 100, nice multiples, again, factors of 10, to find the Celsius scale, so it kind of went with the metric system. Everybody could find water, and they could boil it and freeze it and find the same range for their thermometer, so we could all set our thermometers to the same rank. The Kelvin scale came into being when scientists discovered the correlation between temperature and volume for certain gases. When they were studying this, they saw that as the temperature cooled, the volume went down, and it ended up that those volumes became negative numbers, which is impossible. We cannot have a negatively sized container. And so we had to change to the Kelvin scale so that there wasn't negative sized containers, but rather just smaller sized. And so it ended up that we saw that we could lower the temperature. In this calculation, they found this new temperature, which was the coldest possible temperature, and that is the temperature when all motion stops. So we have never yet reached absolute zero, which is the coldest possible temperature. We've never gotten there yet, but if we did, all motion would have to stop. Now notice that is negative 273 on the Celsius scale. You will be expected to be able to convert from Celsius to Kelvin and Kelvin to Celsius. So let's talk about the basics first. If we're going to go from Celsius to Kelvin, the number is going to get larger. So for that, we're going to add 273.15 Kelvin. And then, to go from Kelvin to Celsius, the number has to get smaller. So whatever temperature we have in Kelvin, we're going to subtract 273.15 to find that temperature in Celsius. We're going to see some problems next. We are going to use 273.15 because it is a more accurate number. Let's start by converting 50 Kelvin to degrees Celsius. We're starting in Kelvin. Notice that there is no degree symbol on the Kelvin. That's the common terminology. We don't put a degree symbol on Kelvin. So we start with our 50, and we're going to go to a smaller number, so we're going to subtract 273.15, which is equal to negative 223.15 degrees Celsius. Notice that negative numbers are okay for Celsius temperatures. Now let's convert 25 degrees Celsius to Kelvin. All we're going to do is take our 25 degrees Celsius, add 273.15 to get the answer of 298.15 Kelvin. And that's all there is to changing from Kelvin to Celsius and Celsius to Kelvin. Let's look at what temperature actually measures. Temperature measures the average kinetic energy of the system. Kinetic energy is related to both mass and speed. If we look at a container full of the same particles, they will all have the same mass, which means that the kinetic energy will be related to the average speed of those particles. We're going to see a short clip, and I'd like you to observe what happens to the speed of the particles as the temperature is lowered and then raised again. These gaseous water molecules are starting off at 90 degrees Celsius, and now we're cooling them down, and watch what happens to their speed. Hopefully you can see that they are slowing, going slower and slower. We get down to about 50 degrees, and now the temperature is going back up, and hopefully you can see that the speed of those particles is increasing. Again, all of these have the same mass, so we're not changing the mass. So as you can see, the temperature measures the speed of the particles if it's all the same particle. Let's look at an example of how this might affect something in your daily life. In this example, we're going to have some cold water and some hot water. And we're going to see what happens when we add food coloring to it.
Make them move faster. On the left jar here I have some cold water. I'm going to put just a drop of food coloring into it. And on the right is some hot water. I'm going to put a drop of red food coloring into it. And just kind of watch them and look for a difference. We're still talking about particles, those little tiny things that everything is made up of. Too small to see, but when we put the food coloring in water, we can actually see the motion of all the different atoms. And we can now start to talk about how we can change the motion, what it means to have, for one thing to be hot, one thing to be cold, what that actually means in terms of the particles. I think it's pretty evident here to see that there is more motion in the hot water, and that temperature is merely a measure of motion. So in our particle diagrams, we're going to start to not only depict numbers of particles and spacing of particles for mass and density, but the energy that the particles have, their motion.
So overall, you should be able to see that the higher the temperature, the faster the particles move. That's true for gases, it's true for liquids, it's also true for solids, although we won't be showing an example of that. So let's think about how we might draw that change. What does temperature measure? Temperature actually measures the average kinetic energy of the system. If you're measuring the water, you're measuring how much average kinetic energy that water has. If you're measuring the air, you're looking to see how much average kinetic energy that air has. Not every particle has the exact same kinetic energy, but we're looking at an average. I'd like to show you a simple representation of the average kinetic energy of these particles. As we've seen, at low temperatures, the average kinetic energy is low, and so we find that the particles tend to be moving slower. As we add energy to the system, the particles move faster and faster, and the temperature rises. And how we model that is with these lines behind the particles. As you can see, the longer the line, the faster we're indicating that this is going. This is sort of like the way a cartoonist might depict speed, like Superman or something like that. So that's what we're going to use as our model of showing how fast something moves. You may want to use this in your lab experiments. You might notice that those lines are going in many different directions, and that is what we expect. These particles will be moving in all sorts of different directions. We'll be talking more about that later in the unit.